Now it's my great pleasure to introduce our speaker today, Dr. Madhur Behl. Dr. Madhur Behl is an associate professor of computer science and system and information engineering at the University of Virginia. He leads UVA's Cavalier Autonomous Racing Team, the winners of the 2024 Indy Autonomous Challenges, and co-founded the F1 10th Autonomous Racing Platform. Dr. Behl earned his PhD and master's degree from the University of Pennsylvania. He is an IEEE senior member and NSF Career Award recipient. Without further ado, please join me in welcoming Dr. Madhur Behl.
Thank you, BC, for inviting me. And it's really great to see familiar faces, but not in pit lane in this setting. So you will see in the next hour that the kind of work I do in the last 4 years, it's fair to say I have probably lived in Indianapolis about 6 months out of those 4 years, but this is my first time coming to Lafayette and to Purdue, and I'm really excited to share what I've been up to and have a discussion about what do I mean by bringing AI up to speed. It's not like AI has slowed down. If anything, it's just crazy fast. It's impossible to keep up with what is going on in AI every day. So allow me to explain what I mean by bringing AI up to speed. And so we can start with a rhetorical question. You don't have to answer it, but just sort of think about it. And the question is, which of these tasks? Okay, not a great start. Which of these is a more intelligent task? Right? Is it to be the best player or a grandmaster at playing chess, a board game, or is it being able to just drive day to day? And it's not a fair question to ask. I haven't defined what more intelligent means here. Obviously, these are different tasks. They require different skills. But if you think about it, chess is this game which requires reasoning and anticipation, strategy, memory, pattern recognition. All of these could be attributed as being intelligent behavior. But you could also reason that driving is a different kind of intelligence, which is sensor, motor skills, and all of that. Right, so if we just maybe do bean counting as a way to establish which is more intelligent, there are only a handful of top-level grandmasters at this game in the world, but there are billions of people who know how to drive, right? So just based on that, it might be you might be inclined to agree that to become the best in the world at chess really requires a different kind of human level intelligence, and driving also requires intelligence, but maybe not as high or not at the same level. So now we can ask the same question, but in a different flavor. And the question would be, well, which of the same two tasks is more difficult for AI to solve? And you can already see where I'm going with this, because the dichotomy is very blatant. On one hand, chess is fully solved decades ago. You can buy for a grand price of $0 an engine called Stockfish from GitHub, and it will be more stronger at playing this game of intelligence than any human that has ever played this game and likely will ever play this game. And Stockfish is not even the strongest engine. Still, it is just beyond the capability of any grandmaster. So what about the other? Can we say the same for driving? Certainly not. Right? Despite all the advances we have made in autonomous driving, and the deployments are happening in various pockets in the country and all around the world, these cars are known to get stuck and cause nuisance in traffic. And it's not that this is just some edge case or some weird situation. They're making the kind of mistakes that no ordinary good driver would make a mistake. Right? We wouldn't be perplexed by just steam coming in from the vents on the road, but these cars are confused by that. And it would be fine if it was only limited to just nuisance and this occasional traffic jam, but unfortunately, this is not the case. Autonomous driving has resulted in very notable and visible injury and harm to both property and life, and in many cases, just loss of life. And so this is a problem, right? So we don't have AI capable of doing what humans can do in driving. So what can humans do when it comes to driving, which is non-autonomous? Like I flew to Indianapolis, I went to the rental car company, I picked up a car that I had never driven in my life before. And I didn't even know which car I was going to get. But within 5 minutes of just accumulating and adjusting the mirrors, I'm good to go. I drove here 1.5 hours, no big deal. And you all have done the same. So humans are effortlessly good at driving, but AI is not. So this is where we begin our real inquiry of why is it that AI can solve the more intelligent game of chess, but still struggle with something like driving. And the answer is, of course, very, very technical and complicated, but to give you the most high-level umbrella of an answer, you can simply say that chess is a closed system. Yes, it is complicated. There's a lot of permutations. There's more board positions than the number of atoms or some kind of analogy there. But it is closed and it's deterministic. So given the state, you could calculate and numerically score the outcomes. And this is what DeepMind did a few years ago with reinforcement learning. And they designed this AlphaZero, which is even more stronger than the other chess engines. Driving, on the other hand, is an open system. And you can say, well, Madhur, what about traffic rules? It has rules. There's laws in traffic. And yes, there are laws in traffic, but those are not the kind of rules which limit the dimensionality of the traffic situations that could arise. Well, first of all, people don't follow the rules. If, like you can see in the video, I don't even know what is going on here, but this is what you have to deal with, right? It's unpredictable, infinite variables, and that is what makes this driving extremely difficult to crack, and you cannot use your chess magic on autonomous driving. So to formalize this notion, which will be the basis of what I do, we can think in terms of this coverage complexity. So you can think this infinite dimensional hyperspace with many, many axes, and I've consolidated some of the axes to, we can think about this infinite space because we can't really think beyond 3D. On one axis, you can have all the different objects you will ever encounter on the road when you are driving. Right, so you have cars which are shaped like hot dogs, or people dressed in Halloween, which is in the news every year for some reason. Whenever it comes Halloween, you see autonomous driving and people, dressed as witches putting cones on the Waymo and all that stuff. So you have to enumerate all of these objects. It's impossible to do, but let's say you do it to the best of your ability. That's not even 1/3 of the space. The other axis is all the different environments in which these objects appear, whether during the day or at night, in rain or fog or snow, under glare, or all the different combinations of every object, every single environment. This is already blown up. And this is what perception is trying to solve. Can we not make mistakes and identify the right object in the right environment and all environments? And even if for some reason you are confident that this can be tackled, the next axis is basically an explosion in time. How these things interact with each other over time is what a traffic scenario is. And so that axis alone is uncountably infinite in some sense. And so this infinite space is what we have to cover if we have to guarantee human level driving intelligence, because I can cover this space pretty well. And you can cover this space pretty well. But what is happening in the AV industry is they are operating in little pockets of this space. One pocket might be Bay Area, another might be sunny day in Phoenix, another might be Austin, and that's what is called the operational design domain. So within these conditions, we can operate. Outside of these conditions, all bets are off, which is fair because we have to be safety first. We can't recklessly just go and exploit this. But AI, at least in the last 36 months, has done pretty well when it comes to other kind of open systems. Right? For example, consider natural language. It's definitely more open than chess. And you are no strangers to what has happened in NLP. You can take your choice of what AI agent you use, and it can understand all different languages on the planet, including programming languages. And so this is just remarkable progress. And if you dig deep into how this was accomplished overnight, the answer is that it was trained on internet scale data. ChatGPT pretty much has scraped every piece of text that was ever produced by our species. That's what it took to train and feed it on this transformer machinery. Of course, I'm oversimplifying. It's more than just a single transformer, but you get the idea. The same thing has happened in computer vision, another open world problem. We are beginning to see remarkable progress in computer vision. Right? You can see these cluttered scenes, and this open source model called SAM2 from Meta, it's doing pretty well. Probably doing better than what I could do to segment the scene myself. And you can also imagine how this could be useful for something like autonomous driving, because you need to understand the space of objects and environments, and this is progress at the end of the day in that space. And how did this happen? Same trick. It was trained on internet scale video data, annotated video data. Because we had so much data, the computer vision community has existed for multiple decades. They have huge data sets. And so, yes, there have been remarkable advances in not just generative AI, but AI in particular in the last 3 years. But what I want you to think about is most of these recent advances, which have shown this emergence intelligence for open systems, they are confined to the digital world, to the virtual world. They can manipulate content, generate video, text, audio. They live in the Twitter sphere or X sphere or whatever it's called today, right? And as a computer scientist, when you think about artificial intelligence, yes, language is an intelligent attribute. Vision is also what makes and contributes to our intelligence. But the thing which is missing, or what we have started to realize and emphasize, is the third pillar, without which you cannot have general intelligence, is what you all know as physical intelligence, which is very difficult to just define. So it's a collection of many different things. It's basically the understanding of the world. I can close my eyes and pick up this bottle and I will know there's liquid inside of it. How am I able to do that without vision and language? It's my physical understanding of the world around me. That's what happens when I drive. I'm almost simulating the world as I drive without making a conscious effort. And I just do it. We can all do it. So why can't computers do this? They're stuck in this digital world. And so we have to bring this AI intelligence from the virtual world to the real world, right? So we have to bring it out of the matrix to the real world. That is the pending challenge. And so the roboticists like myself and others around the world, they are also trying to see whether the same trick will apply. But what is the data for the physical world? Which data set represents all of your innate knowledge about physics? It's very difficult. And so this is what has been happening in the last year in robotics. People are collecting manipulation data for domestic robots to try and solve the problem of general intelligence for robotics with the same tool, with the same kind of ideas that have worked for language and for vision. But time will tell whether this is the right path. We don't know yet. It's too early. That being said, it's too early. This is still the best time to be working in robotics and autonomy. Ever since I started in this field, I have my biases, but this is truly one of the best times in robotics because it has really boomed as a field, not just autonomous driving, but all different kinds of robotics, aerial, grounded, legged, what have you. So this is what I'm broadly interested in. I want to advance physical intelligence, but I will show you today you could advance physical intelligence without spending all your time building foundation models, right? So I don't have anything against them, but you should learn and build things from first principles, and they sometimes do work. And so autonomous driving for me is nothing but a test bed for physical AI at the end of the day. In fact, I want to make a case it's one of the best test beds for physical AI. It has all the attributes you need in terms of the interaction, the explosion, the coverage, the safety, which all AI algorithms have to have. And simply put, by some measure, I would say autonomous driving cars or even driver assistance systems are already the largest volume of robots deployed on the planet. So you have the most data if you wanted to go after data. So solve this problem first before you start building new hype cycles of that we can solve all of robotics. So this is why I have focused in my group to work on autonomous driving. It's a huge space, largely unsolved, despite all the progress. And today I want to talk about some broad level ideas of what my group does to give you the intuition for which problems I'm going after. You may not like or even agree with the solutions, but that's not even my goal here. My goal here is to just share the problems that we should be going after, right? So my first problem is going to be, how do we even measure autonomous vehicle safety? We'll talk about then, if you can measure it, could you possibly improve safety of an autonomous vehicle? How do you drive always within safety limits, because it has to be safe at the end of the day. And finally, we'll talk about how do you design intelligence in autonomy that can handle unexpected traffic situations. Okay, so we'll do like a rapid pass through each of these, and you can always ping me if you have questions about the deeper details. So with that being said, let's dive into the first one. How do you measure autonomous vehicle safety? Okay, back to our picture. Let's say you have two autonomous vehicles, A and B. They could be from different companies, Tesla, Waymo, Cruise unfortunately doesn't exist anymore, but it could also be two different vehicles from the same company with different software versions. They are two different autonomous vehicles. They are operating in different situations. And the question I want to pose is A more safe than B? Very simplest question. And you would be surprised, or maybe not, that despite 2 decades of research, we have zero answer to this question. We don't know how to answer such questions for autonomous vehicles. And it is very difficult because we don't know what safety is. There is no measuring stick for safety. The industry will roll off reports and numbers about disengagements and miles. It's pretty well established that they are not meaningful metrics of true safety of an autonomous vehicle. They are just measure of some high-level, fleet-level performance. It's not the true measure of safe progress. So how do you measure this? How do you say, if I have two vehicles, which one is safer? It's a very difficult question to answer, and so our hypothesis is, in my group, that in order to answer this, let's answer a second question first, which is, if I am given two vehicles, can I observe them in the same situation? Because if one vehicle is in Austin, the other is in New York, how will I compare their safety? I need to observe them in the same traffic scenario, and then maybe there is some scope of statistically determining, well, humans do this in this situation, and this car did A, B did something bizarre, so we should look at B. Let's start there. Very reasonable idea. So that's what we did, right? My goal is that if you have data, huge data from an autonomous driving company called Driftic, and you have some scenario of interest, in this case, how does their car behave in tunnels? The goal should be, if we go and look at data from other autonomous vehicle companies, Goo Drive and Eigenwagon, can we just automatically find the similar situations given this reference traffic scenario? That's the question we want to solve in order to have some hope of solving the real question that I still don't know how to solve. So this is what we have done. We have devised a method which we call scenario to vector. It's inspired from natural language, which has word to vector or sentence to vector. So scenario is the high dimensional information about what is happening around you, what agents are there, what is the geometry of the road, where is the traffic light. Right, so it's not just limited to the visual spectrum, it could be more than that. But we started with the visual spectrum, and we have published work where basically we showed that this is somewhat possible to learn. That if you give it some base reference scenarios in a corpus of video data, you should be able to find similar situations for different autonomous vehicles. But we very soon, and we do this not just in some uninterpretable space, because we care about the main question. The way we have done this is we introduce some human readable, human understandable embedding or a description language, which basically breaks down the actions of every single agent over time. What did this car do? Did it merge right? Did it do this maneuver or that maneuver? So that at the end of the day, when you say these situations are similar, you can see the proof in the pudding and convince yourself that, yeah, both of these things are doing, it's similar because of these reasons, so to speak. So we've done this for video data, and then realized that actually there's a shortcut here where you don't need to do pixel level similarity or that's not what we are after. a right-hand merge is still a merge no matter what time of day it is. So we are not biasing this method to video similarity. It's different from video similarity. It has to understand the spatiotemporal kind of agentic level information inside this video. That's the challenge. And so what we have realized is that we can do much better in terms of accuracy when we get rid of the perception altogether and directly work with trajectory level data. And if most of you may already know this, that autonomous vehicles, they have a perception layer which feeds some understanding of the world to a planner. And that understanding of the world looks like this. What is happening all around me? And you can just operate in this space and still try to solve this scenario similarity problem. And this is what my student and I, Aaron Harder, have been working on. We have this framework called Trajectory to Action Pipeline, which is trying to solve this scenario similarity problem in order to have an attempt to solve the bigger safety problem. Okay, so that's all I will say about this work. Let's jump on to the next problem. How do you improve AV safety? And let me lay down the idea here, right? So once again, we have an autonomous vehicle operating in its pocket. As you all would agree, it makes so much more sense to simulate various pockets in this infinite space rather than to actually go and deploy and figure it out and leave it to chance to encounter some situation. Could we deliberately generate these rare situations in simulation? That has been a question which has been looked at by researchers recently, but it's not just any rare situation. What we want to do is we want to generate these scenarios in simulation this time that can cause a deliberate crash with my autonomous vehicle. Because if anytime I can cause a crash, I've discovered some situation where the AV might have failed. Considering there's some disclaimer here about who was at fault and all that subjective stuff. But this is what we want to do. We want to generate scenarios that can cause a crash in simulation with a given autonomous vehicle. So let's say Waymo gives you, they will never give you, but let's say they give you a Docker image of their planner. Your job is to falsify that planner. That's what this problem is. But the problem is more interesting because you want to automatically falsify this planner. It's very tedious to manually think of these. What if the planner is a black box? And so this is the work that one of my other graduate students, Amar, has been leading. And so we have a framework here. It's very aptly called Crash, because that's the goal of the entire project. And the idea is quite interesting. Somebody gives you an autonomous vehicle stack in a simulator. You don't even touch their stack. You let it run, or as my undergrads say, you let it cook, and then you let it do its thing. But what we will do is we will control all the other traffic agents around the ego vehicle. And we will incentivize the NPCs, the non-player characters of this video game, to try and cause some nuisance with the AV's goal, interfere with its goal, to kind of test the waters. Right, so this is getting into this realm of multi-agent inverse deep reinforcement learning and in the adversarial sense. And this is still early days in this work, but what we have been able to show is you can craft very, very simple. You're not like over handcrafting some specific reward. Very simple reward that try to make progress towards the other agent and try to cause a collision. So like a continuous term and a sparse term. And then the goal of the NPC agent is to falsify. And so you see here that it has learned very easily. It's a very toy example that I have to just speed up and rear end the ego vehicle because the ego vehicle doesn't know what to do. But then the key idea is once you do this, we want to also improve the safety of the ego. So once you are able to falsify, let's flip the script. And this time, let's train the ego vehicle to avoid this adversarial scenario. So now in the bottom scenario, this NPC is still crazily trying to cause a collision. The ego has learned very quickly that when the NPC tries to cause this collision, all I have to do is just step on the gas and evade. Because if I slow down, I'm getting rear-ended. So there is obviously deeper questions about how realistic these are, the saliency of these and the scale of these. But like I said, the key idea behind this method is what I am calling safety hardening. Because after doing this work for many, many years, I have almost, I say almost because there's some room for changing my opinion, I've almost convinced myself that it's impossible to give hard guarantees in this world. So all you can give is statistical hardening guarantees, and that's what we can give. We can repeatedly do falsification hardening, and see that could we learn the grandmasters of evasion and attack. Right, that's the goal here. And so again, I won't go into details, but for those of you who are into RL, this becomes super dense just with 2 agents. There's like game theory, and it's a beautiful problem that I would love to geek out with you, later. But that's what we have done. This is a paper that will appear in a workshop at AAAI a couple of months from now, which shows that this is very effective in falsifying. You can easily falsify any rule-based or even learning-based planner, and then the hardening actually is effective to teach the ego vehicle how to not fail to this adversary. But like I said, this is preliminary investigation of the problem. We obviously have to scale to some more meaningful geometry and more. We also want to address the problem of who was at fault. So we are thinking of doing targeted collisions, not just any collision, but maybe I only want to look at side swipes. Can you just generate all side swipes or rear end, or a specific type of collision? Can we engineer that? All right, let's keep going forward. This is a pretty fast-paced overview. The next one is how do you drive within safety limits? And there would be no discussion complete in physical intelligence without appreciating the physics of the problem. And that's what this is about, okay? An autonomous vehicle has known vehicle dynamics. People have spent their lifetimes trying to describe these things. Drivetrain dynamics, tire dynamics, aerodynamics, and suspension geometry, how it affects the dynamics of the vehicle. And I am a computer scientist. I did not know any of these, but I learned, and my students learned all of this, because this is what it takes to build intelligence that can respect this physics. Right? So it's the problem with known dynamics is it's very difficult to tune these parameters of these models. They are nonlinear functions. You can do some data fitting, but you are still going to be always off. Right? At the end of the day, it's just very difficult to tune these models, even if you know their exact ordinary differential equations. And so this is where I have done a lot of work. My group has produced a lot of different ideas, including how can we just bake this physics inside a neural network and directly learn the dynamics from data, both in an offline and online manner. That's a paper called Deep Dynamics, which appeared in Automation Letters a few years ago. And then there's a series of very mature work which is about Gaussian process learning, which I will show you what that does in a second. But at the end of the day, the only reason why you could be safe is that you are certain that you understand the underlying physics of the car. And that, for us and for my racing team, which I haven't described yet, so I'm jumping ahead, that really means understanding things like GG diagrams and tire dynamics and slip angles. And we have modeled all of this in as much rigor with as much machinery from the research that I will reveal shortly, and that's what this physics-based learning has to be done, because how else will you be physically intelligent if you don't know the true physics, right? At the end of the day, my boy Newton has said that the car moves forward because the tire rotates and presses against the road. So you have to understand that. Otherwise, it's GG, game over. Okay, so just to give you a glimpse of what one idea is, this is what is called deep kernel learning for Gaussian processes. This is a work by Jinyun Ning. And let's not get bogged down with the math. The idea is you have some complicated model and you have your best guess of the parameters. There's always going to be a discrepancy between what you think is the true physics and something that you never modeled, right? So we call this discrepancy residual. And the idea, which itself is not new, but its application to vehicle dynamics and specifically the merging of deep kernel learning with GPs is very new. What we have shown is on real data from real autonomous vehicles at high speeds is that you could simply learn this residual using Gaussian processes, but Gaussian processes are very painful to get right, and so you have to, in this case, tweak the machinery of Gaussian processes by marrying it with deep kernel learning. So use the AI, the good part of AI, but then at the end of the day, feed it into some physics-based model that you know for certain is going to work. And that, in my opinion, is a very good, safe bet to ensure that your AI doesn't make non-physical outputs which cannot be realized by the actual robot. Okay? Let me quickly glance at how we are doing on time. Perfect. Okay, so this was a pretty dense but fast-paced walkthrough. Let's keep going and touch upon the last part, which will take the most time as well. So let's get to it, right? So the last question on my mind was, how do you handle or make a AV handle unexpected situations? Very, very difficult, okay? I don't have a complete answer. I'm being upfront and honest with you. But let me share the story behind our investigation into this question. And my story really begins over a century ago. When the first automobiles were invented, there was a transition in society from horse-drawn carriages to what people call horseless carriages with engines. And there was skepticism in the public that, is this new horseless carriage safe? What is this brake that you speak of? What is the steering wheel? I'm more confident in managing the reins of my animal rather than this contraption you have presented to me. There was true concern in the public's mind 100 years ago, more than 100 years ago. And among other things, motorsport racing truly was invented by the automotive manufacturers, of course, to sell more cars, let's be real, but to convince the public about the underlying safety and endurance and performance of this new technology. To show that at high speeds, these drivers could do things. Yes, it became a sport and entertainment and Formula One, all that is true. But at its core, motorsport was always the incubation ground for automotive industry. Things that you and I take for granted, like a rear view mirror or a seat belt or some brake material, you can probably trace its origin to some innovation in motorsport at some point. Let's fast forward to this decade. And I submit that we are undergoing another transition in the history of mobility, early days. This time we are going from driver-driven carriages to driverless carriages. And similar questions of safety have resurfaced. Is this good enough? Is this safe? All the previous half of the talk basically was all those questions. And so then, given this history, it wasn't that difficult, but at the time it seemed like a crazy idea to propose, well, then let's just use racing to improve the safety of autonomous vehicles. And so this idea we brought forth, we termed it called safety through agility. And we were not suggesting that you have to race through traffic in order to be safe. Maybe in some cities, it's probably a good idea to do that, but that's not what the goal was here. The goal was that, could we learn the skill of these drivers, how they operate in high speed, close proximity of each other, yet they don't crash every so often, and they always are able to drive and sometimes even exceed the limits of that GG diagram, the tire dynamics, and still keep it together. How are they able to do it? If we can learn that, surely that can help advance the ability of autonomous vehicles to deal with uncertain dynamic situations. And trust me, I grew up driving in India. I know a lot about uncertain dynamic traffic situations, right? So that was the crazy idea. And in retrospect, it's not that crazy, because if you know this, the entire autonomous vehicle industry began with a race. Okay, 2 decades ago. There was a race that has the inception point of the entire AV industry, which some of it doesn't exist anymore, but existed at some point. So this was my goal. Can autonomous racing advance safety for autonomous driving? Hyperbole, pipe dream at the time, but we ran with it. And growing up, I was a fan of this show on Discovery. I don't think it's aired anymore, but maybe you can find it on YouTube, called Mythbusters. And what I've learned from that show is what Adam Savage, Jamie has taught me, is before you try to do something crazy, try to do it on a small scale first and see if the idea has any feet. And so I literally embraced this philosophy, and I didn't have a Formula One car, of course, to do autonomous racing. So I went ahead and designed a 1/10 scale autonomous race car, which I named Formula 1/10. This was when I was still a grad student at Penn, and I was transitioning out of Penn. I was done with my PhD. And so we made this RC car autonomous by putting some NVIDIA sensors, a LiDAR, some motor controller on it. And so here you see some footage of us assembling the very first F110 car is born right here, the time-lapse video. We made a video of this car doing laps on our lab at Penn at the time. I prepared IKEA-style instructions so that anybody could replicate this work. And so you could just laser cut with MDF or ABS material and create these chassis, and you would have your own autonomous car. But that still, there was too much friction for other people to reproduce this. So I literally taught the entire course on F110 autonomous racing and put all the lectures on YouTube so anybody could follow it. And then slowly we realized this is actually fulfilling a need, because researchers, they did not, at the time at least, have access to full-scale cars to do their experimentation on. So this was, a very easy way to do research in a controlled environment in their labs. And so that's what happened. We started seeing researchers use the F110 cars in their research labs, from control to verification to real-time systems to wireless communication. You name it, and probably there is some paper out there which has used F110 to try and demonstrate the efficacy of the idea at smaller scale. And I'm guilty of doing it. My lab has probably more than 24 F110 cars. I still teach this course till date. And so while this was happening, this was growing over the years, it was very clear to me that we have to race these cars. Right? That's the obvious thing you do when you have any kind of autonomous car, and it also hinted back at this crazy idea that I wanted to pursue. So I started the F110 Autonomous Racing Grand Prix. We started hosting these together with my advisor at prominent cyber-physical system, robotics, machine learning, embedded systems conferences, and this is something which has continued till date. Hundreds of teams over the years have participated in this. Probably more than 1,000 students have at some point come to a conference and raced and learned something, and the scale of this has grown beyond what anyone would have imagined at the time, and it continues to grow. Right? Last year we had 6 races. This year we might have 7 races at different countries happening at the same time in some cases. So this was great. We had some means to test the waters, but this wasn't the autonomous racing where I could learn from the experts. So we still had to solve a problem, right? So how did we train AI agents for autonomous racing? Still didn't have a Formula One car, so only a F110 car. So what we did was we resorted to video games. So this is the Formula One game from a few years ago, and this is the real footage, and that's the game footage. And if I had not put the labels, it would be pretty indistinguishable to see which is real and which is a simulation or a game. So why reinvent the wheel? Let NVIDIA and all these code masters, they've done so much work to bake the physics and the graphics. All we had to do was take this $30 video game and convert it into a ROS2 simulator. So that's what we did. We wrote an API called Deep Racing that could take the state information from the game, and you could run your algorithm, and with the Python script, you could drive the car without actually playing the video game. So this was Deep Racing AI, and this became the basis for a whole lot of research over the past 5 years, which I will not go all into, but I will give a shout out to my student Trent Wise, who was going to graduate in summer this year. But essentially, his research is the answer to this question of could we learn from racing, and what can we learn? What kind of motion planning, what kind of overtaking could we learn from racing? I'll share the key idea of his research and maybe leave it at that. The first thing to try is what everybody was trying at the time, which is what end-to-end control. Just feed in the image and let the neural network decide what to do. This is already in violation of what I said earlier. We need to bake in physics. This is violating that, so it did not work, right? So the car doesn't recover. It has no way to recover once it has made a mistake from its feed-forward open loop kind of prediction. So a better idea is the following. Instead of letting the neural network control the car, the job of the network should be path planning, and let some model-based controller control the car so that the car doesn't behave wildly. And so this is what we did. So the car can drive around, but you can see it's cutting corners left and right. Right, so the neural network is taking in the images, it's predicting a sequence of waypoints that the car should follow, and for the most part it's fine, but it cuts corners. So why is it doing that? Of course, it has no knowledge of the corners or anything. It's just doing what supervised learning is. So what is causing this bad behavior is there's just too many things to predict. Every waypoint is 6 different numbers: X, Y, Z, heading, velocity. So if you are predicting 100 waypoints, you're basically predicting, 500 numbers. So you can get them wrong, right? It's a high dimensional problem. So the fix that we applied, which is the key basis of the entire research in this area in my group, is the following. You don't need to predict all these waypoints. It's just too much work and too many things to learn, too many things to get wrong. What you can do is just learn a low-level representation of this. So instead of predicting hundreds of waypoints, we basically predict the full curve using just a few control points. So we represent the trajectory as a Bezier curve, which is a special kind of a spline. And just to give you a 101 on Bezier curves, each of these red curves, which are curvy, they are fully described by the gray dots, which are the control points of the Bezier curve. So you could define 1,000 points using 5 numbers because you just have 5 control points. So it reduces the dimensionality, and Bezier curves basically gives you very smooth trajectories. And later, much later, I would find out in my wiki, one of the days where you go deep into Wikipedia, that Pierre Bezier, who came up with Bezier curves, he used to use these curves to model the curvature of body panels on Renault race cars. So at some level, there was some connection to racing always. We just rediscovered it through a very bizarre accident. So these Bezier curves are low dimensional representation. They have very, very nice mathematical properties that you can exploit, and then you replace your waypoint prediction with Bezier prediction, and you solve this corner cutting nonsense, right? The car can now basically go around Australia, and it's racing like a good amateur Formula 1 driver. Maybe not the best one, because it's still relying on the data it was trained on. So it's limited by the limitations of supervised learning, but it's doing pretty well. Right, so this is what we wanted to fix. You are limited by, you have some data, which was basically trench driving in my lab, and then the neural network trying to reproduce the Bezier curve for the car to drive. Good, but not great. So the performance is limited because I don't have access to Lewis Hamilton's data, but we did try to get some eSport data at the time with some collaboration with Sony AI. And so this is the Bezier curve. So what we can do instead is just do some clever tricks on the output side. And here is the trick which has now made this work into, basically it can solve not just trajectory synthesis, it can solve a prediction and multi-agent planning. That is that the curve could be a distribution of trajectories. You don't have to predict a single curve. The control points could be Gaussian distribution. So you could sample from this distribution. Every sample from this distribution is a race trajectory that you can take. So if those of you who are into robotics or state estimation and you know what a particle filter is, this is basically a particle filter, but every particle is a trajectory now from this distribution. And so what you can do is, instead of a fixed control point, you have a distribution which you learn from your original data. But when you sample from the distribution, chances are you can still generate something which was not present in your original data. That's the whole idea. So you are not limited by supervised learning. And when you sample a curve, you can score it. You can say, no good, it's violating the track bound, reject, next sample. Or no good, the car cannot make this maneuver, it will spin out, next sample. You can keep doing this until you have the optimal sample with some compute limit that you throw at this problem. And that has been solved in robotics. You have like adaptive Monte Carlo methods that can deal with this kind of numerical setups. So that's what we have done. We can take this Bezier curve, we can make a distribution and score these samples, the gray samples, until you get in real time the actual race line, which is feasible, fast, within bounds, and you pass it to your model-based controller. And so this is the way. That was the name of the paper. So I think this came out when Mandalorian was in the news or something. So this is called differential Bayesian filtering. And this is very promising. Immediately, you can get lap times which are very close to actual lap times of real Formula One drivers on the same track. Just with some amateur training and sampling, you are exploiting this power. And so this method is so extensible that you don't need to rely on this imaging stuff. It's too limiting, in fact. You don't need to train on the input as the image. You could just feed it trajectories, any kind of representation. So you can basically do the entire thing without going into perception at all, which is very, very useful. And the same machinery is now being used to do prediction. There's no difference between my trajectory and predicting an opponent's trajectory. So we just basically replace the state history with the opponent's state history, and the output would be the future position of the target vehicle. So very, very excited about where this can lead. This is probably too much information for me to explain. I won't even try, but we can learn the velocity profile of the opponent using not just one curve, but something called a composite Bezier curve, where you have more than one curve stitched with each other. Okay, enough about Bezier curves. So this is my introduction to these problems, because I don't have the final solutions yet. I'm still trying. But what happened to the goal of racing? Is it done? We have Bezier curves and this game, and should we call it off? No. So the next thing we did is we went from 1/10 scale vehicles to full scale vehicles. I really got an opportunity, like the Purdue AI racing team. In 2020, I started the Cavalier Autonomous racing team as part of this competition called the Indy Autonomous Challenge. And at the time, we were just one of 9 universities in the world which got to participate in the inaugural race at Indianapolis Motor Speedway. This is a real Indy race car. It's an Indy Lights car for those who speak Indy. It's a Dallara IL-15 chassis. At the time, we worked with a racing team called Juncos Hollinger Racing. They helped put this car together along with students from Clemson. And so this is full-scale autonomy. This is my dream getting realized in some sense, because all these years we've been stuck to the F110, doing progress in the video game. Now it was our chance to try it out on the real physical AI. And so this was full-scale autonomy. It had all the LiDARs, the NVIDIA compute, radar, camera, you name it, all decked up at the time. All we had, and every team had the same car, similar. And so all we had to do, I say all, is we had to write the entire software stack for this car. That was the competition. It's a battle of algorithms. And so these are some highlights from that very first race. Right? On a good day, Waymo will go the speed limit of the road. Here, this car is going out of the pits at 90 miles per hour. And it's figuring out how to warm up its tires, how long. It's measuring the temperature of the tire, feeding it into that Pajeka model, the tire model, and figuring out, I have only 3 laps remaining. Should I speed up if I want to warm up more, or should I just maintain what I have been asked to do? And so on this day, it was a cold winter morning, and we hit 126 miles per hour, which was not enough to win $1 million on this day, but it was enough to give us some visibility of becoming the fastest American team at the time. And looking at it, you know, if you are into autonomous racing, you are already impressed. But if you're not, I'm with you. It doesn't look that hard. There's one car on the track. What could be that so difficult about it? It's not trivial. Okay, many things can fail. Here's some snippets. Localization could fail. Your car doesn't know where it is, so it just veers into the infield. Or your controller is unstable. It's giving some steering input that is causing the car to shunt into the wall. Or nuance failures can occur. This car hits the wall, they should just stop now. It should know that I have hit the wall, I should stop, something is wrong. It doesn't realize that and continues to go until just physics takes over. So every single thing can go wrong, and that is the challenge of autonomous racing. At high speeds, everything is just harder. Perception is harder, localization, mapping is harder, planning is harder, control is definitely harder. So our goal was to master the oval track. We started with Indy, and over the next few years we've raced at many different tracks in the country. And not just that, the competition also evolved from single car racing to two car racing. But you can't just show up and do two car racing. You have to build capability incrementally to that level. So let me share some steps that I think even the Purdue team did recently that you have to do in order to be able to race with multiple cars. Right? The very first is, can you go fast and slam the brakes and not crash your car? Right, so there's a red flag which appears here, and the car just has to gracefully come to a stop. It's difficult because under this load, the steering can wobble and your car can just spin. So the control needs to understand this dynamics very well. If you can do that, if you can go very fast, the next thing is, can you overtake a ghost opponent? So here you will see the car, it's at Vegas. There is no opponent on track, but we are feeding a ghost opponent into our planner, and the car thinks it has to overtake this ghost, and so it will veer out. You will see it will also go up the track in the video in IRL, and it will try to overtake this ghost opponent. This is how we test. This is how we can be sure that if tomorrow there is a real car, we will do the same maneuver, and we will not just go and collide into them. So this is a very important test. Now you are ready. You can go fast and you can avoid ghost. Now can you see the opponent? So there's a test where you have to track the other car, right? So here's the German team, and 40 meters behind them is my car, and you can see on our base station, we see them and we see their prediction as well using Bezier curves and all that stuff. So now you see them, you can overtake, so now let's do a competition, right? The rules of the competition are very simple. It's like a game of chicken in some sense, where there's a speed, I take my turn. If I overtake you, you also get to overtake me at the same speed. If both of us succeed, then we go faster and faster and faster until something goes wrong with one car, or they crash, or the team decides that we don't want to risk a crash. All three possible outcomes. So very quickly, some highlights from one of the passing competitions. This is from 2024, so last year at CES. That is MIT's car, and they are going at 80 miles per hour. And we are just avoiding a ghost, right? We just did this with a ghost. Now it's a real car. It should work. It's the exact same maneuver, the exact same ideas. It's just integration of your perception and prediction along with your planner. Now they are going a little bit faster. This is what you guys did this year as well, which is amazing to see, where you went up to like 150 miles per hour. So it gets trickier because you're running out of time before the passing zone finishes. So your planner has to adapt. It can't do the same choreography every single time. It needs to know that I need to accelerate sooner. So last year we came second, which was a great encouragement for my team. It gave us the confidence that all this time we have spent in simulation and all these, writing these papers, we now finally have vindication that it could work in the real world. But it doesn't always work. Okay? Actually, you can count on it to never always work. So these are some of our worst crashes. This one was probably the worst at 125 miles per hour, just spins into the wall. Here, Auburn is overtaking my team, and then their car decides to just veer into a path. We can't do anything about it. So, same mistake as the very first year. So we haven't learned from our mistake in some sense. Localization failure, and the last one is my favorite. The car is basically a lawnmower at this point.
Oh.
So this is $1 million car, folks. So it's very expensive, or I meant to say very valuable lessons that we have learned from these crashes. And possibly one of my all-time favorite team photos is one where each of my students is holding a damaged part from the car after one of our worst crashes, because that's what we can take away, right? It's in the moment, it obviously is disheartening, and you are so close, and then all of a sudden you can't race, but the fact that you are able to do this at all is just amazing, and that's what we take away, and we look at the data and we try to just improve. So things were going well for my team until another hurdle came my way, and I'll wrap up in another 5 minutes. Can you do this on a new car? I say new because that's what happened this year. They basically overhauled the entire car with a new perception system, new drive-by-wire system, so different steering, different brakes. So this is what we did last summer. The entire summer, my team and I basically lived in Indy and Kentucky, and collectively, I think we drove around 500 miles of testing this new version of the car, doing very, very slow speed tests to see, is the steering shivering, or is it our algorithm still working, to get data to feed into the physics-informed neural networks, the Gaussian processes. That's what was happening in Kentucky. We were gaining a little bit of speed, 100 miles per hour, 120, slowly and slowly. So these are the kind of tests we do on track, right? Every track time is the most limited resource in autonomous racing. So when you get on track, you better have a plan. You cannot wing it. If you don't have a plan, you will not make the most out of that track time. So we knew exactly the test we had to run every single time, and most of the time we were just dialing in our model predictive controller, our models, the knowledge of that GGV diagram, the slip angles. That's what we were doing most of the time to make sure that we have the faith in our methods that the car will do the right thing. Autonomous racing is about one thing: how much confidence you have in your software that if something goes wrong, the car will do the right thing, because you cannot intervene. It's probably, even if you could intervene, you won't be fast enough to intervene. So we rely a lot on simulations. I have probably, this is just 4, but the truth is my group probably has 8 simulators at this point. Many of them we've developed in-house just to test our planner, just to do this overtaking, play out a million scenarios of overtaking, see where it will fail. Crash, reinforcement learning ties it to this problem as well. Use more games, use multiple simulators that the Indy Autonomous team has supported. All of this to culminate to one day, which I will never forget for the rest of my life, and that's what I will share, and then we'll call it off. On 6th of September, we went to Indy for the second time in the history of ISE, this time with 10 teams, not 9. It was a good day. Every team did amazingly well, including the team from Purdue. In fact, the 6 teams went first. All of these teams, or most of these teams, their speed is already more than the winning speed from 2021. That just goes to show how far the entire competition fleet has come. Right? The winning speed in 2021 was at 133 from Toom, and you can already see the teams are doing better than the $1 million speed. So then it was 3 more teams to go: the German team from TUM, my team, and the Polymove team, which has practically won every second race that has ever been held in this competition. They're the defending champions. And just before it was our turn, it started to rain on the track. And many of you might be there, you remember this. And I was there in race control, and I saw this, and I was like, okay, you know what? We went fast yesterday in practice. That's great for us. We're probably not going to race today in this weather, so let's call it off, right? So they did try their best to dry the track. It took about 2 hours for them to dry the track. And they said, it is kind of dry. You can go out and race. It's good enough for you to race at the kind of speeds you want to go. So the German team went first. They already tried to go fast, 166 miles per hour. And as they were pushing, they spin out, right? They're the team who has just gone before us. And so we see this, and I look at my students. I'm like, okay, what's the plan here? Are we sending it, or should we just try to save the car? And I wouldn't lie to you, we were very anxious in the race control room. But we believed in the process. We believed in the data and the science and all this testing that had happened over the summer. And so we said, let's try it. Let's see what the warm-up looks like, and if everything looks good and it's consistent with our simulated lap times, we will stick to our plan. So let me play possibly the best 120 seconds of the broadcast, in my opinion. Of course, I'm biased.
All right, let's see. They didn't need a lot. They did it! 170.645 from Cavalier Autonomous Racing in the University of Virginia. That, folks, was an amazing lap, especially after following a car that had an incident, then a stoppage, and then going out and pushing the envelope like that, Rob.
And they're still going. They're still on it. They're trying to get a little more faster at 171. They crossed the yard bricks over 180 miles an hour.
180
in front of us. So, but they're a little bit slower on the back. We'll see. They're 170 to the corner again. This one's going to be close. They're going to be really close, I think, again. They definitely didn't stop pushing.
Beautiful pattern.
This announcer has the right timbre of voice to make it so exciting.
Wow. There it is.
171.011. They just continue to open it up. What a lap. 2 laps over 170 miles an hour. They do 2 more like that. That's a 4-lap qualifying run here at Indy.
Yeah, no doubt.
That's not bad.
They're shutting that one. I think they're down. They're probably out of time anyway.
Yeah.
So if we would have put this time in 1978, we would have been on pole position, just to give you an idea, against human drivers. Anyways, there was still the Italian team who had to go next, and they were obviously going to push more. Why wouldn't they? And what we did not realize at the time, and now I can reveal, is that 171 should have been 174. That's what the car was trying to do. But the reason it's 171 was there was so much wind on the track that we did not account for. We had never done any kind of wind simulation on IMS. Who would, right? I mean, we already have so many other things to do. So we were counting on Polymove to also send it, and it was a bit of a Ford versus Ferrari moment with the US team against this Italian behemoth. They started off very strong. Looked like, in lap 6 they would certainly be 170 something, which they did do, but that was their fastest lap. So basically we ended up winning the Indy Autonomous challenge. So great moment for us. We set multiple records. 184 was our top speed. This is the fastest autonomous speed on a racetrack. And the interesting part, the beautiful part, the video is great, these images are great. For us, the beautiful part is looking at the data. And when we see that during the turn, you basically are holding 100% throttle all the way. You're gunning it all the way during the turn because there is wind. So you could just floor it and the controller was just stable, and it's just so gratifying to see. There was a passing competition. I will not play the entirety of it, but show you one key moment, because in my opinion, this is some glimpse of safety through agility. That's the only reason I want to show it. So we are trying to overtake the European car.
Oh, that's close. So close here. Cavalier did a brilliant job of recognizing.
So yeah, we almost hit them.
Way too quickly, and the line wasn't there.
And then the commentators are kind of glazing us. Wow, look at that. They avoided them. They almost hit him. And wow, this has never been done before. But this is what it's supposed to do. So I'm kind of glad that it happened. And then the next time around, they are puzzled that they will be like, okay, is this car going to repeat the same mistake in the next lap?
So at this point, again, in what the car's going to do, haven't committed to that outside line.
We're way green again.
All right.
100 mile per hour brackets.
So having committed to the outside line the last time and then having to literally jump aggressively on the brakes, will the car at this point say, we're not going to try that again, we're going to go inside?
I don't know.
Yeah.
So,
That's a fascinating.
fair question, right? Has it learned to do anything better?
First time it gave me this position, it was on the line, I thought I wanted to try the outside line. But it did learn though that car did try to go higher, so it is possible.
It's low here.
Going for the passing the bottom.
Nice. Very well done.
So this is much simpler than it looks. Yes, we did technically learn, but not in the sense that you probably think we did. The thing about racing is, it's a loop. And so every lap, you have information about the opponent from every previous lap. And so your prediction should not only be based on their instantaneous state, but also what they did in the previous laps. And so this is what is influencing the planner in our stack to make a correct prediction this time that they will be very close to the wall. So we should just stay up and not try to overtake on the outside like we did in the previous lap. So this is my favorite picture from the evening. You get to kiss the yard bricks when you win at Indy, and I would like to believe I'm part of some very small Venn diagram of computer scientists who's been able to do that. This, of course, is not possible without the team, the crew, and this is my entire racing crew. It's not just my PhD students. Majority of them are computer science undergraduate students. And some of them are master students, and they do capstones and thesis with me. And my goal is to make it a win-win for them. There shouldn't be a distraction for any student. If they are giving me their time, I better give them grade or pay them, or they should get something worthwhile. While it is worthwhile to be on the track, what is really worthwhile is when these students graduate and then they go to all these places like SpaceX and NVIDIA, and they tell me that they're in interviews. Like, what better job interview than to show that your car did 180 at Indy and that your code was running on it? What more evidence do you need that this person knows robotics? So this is a real great endeavor, and I'm really glad to see Purdue included is pursuing this with full support, and the kind of things your team has accomplished, you should be really, really proud. Being an academic, I believe in sharing everything, so we have released a version of this racing data from 3 years ago called race car data. It's not behind any paywall. You can just go and use it for localization, for prediction. I'm also working on actually getting this data professionally annotated, so it's more useful for everybody and not just the racing teams. But anybody out there, a computer vision person who has nothing to do with racing, should be able to give us their foundation algorithm and try to see, if you can do the physical AI. So what's ahead? It's time to park this car now. I've exceeded my time. As many of you may already know, about 50 years ago, there was a race, a very unique race, which was held. It was called the Race of the Two Worlds, where Indy racing drivers went to a Formula One track in Italy at Monza and raced their Indy cars at Monza. And then the Formula One drivers, they drove their Formula One cars in Indianapolis. And this event, as far as Vicky tells me, was termed Monzapolis. So this is what's going to happen. We just did Indy in 2024. In summer of 2025, we will be at Monza. This will be our first big road course where we will race, hopefully with multiple cars. So we are looking forward to doing that. More recently, we've also combed the data, and we realized, actually this AI driver, it may not be as fast as Lewis Hamilton today. I'm willing to bet money it's more precise than him in some sense. And what we have seen is that when we do laps on an oval at 100 miles per hour, lap after lap, our deviation from one lap to the other lap is minuscule. So the kind of repeatability and precision that you can get from an autonomous racing testing vehicle, whose job is to test aerodynamic parts or wheels for motorsport teams, or maybe even new LiDARs, new RTK sensors. There's something here that we want to explore, and so we're also trying to commercialize some of the experience and the stack that we have created over the years to explore this space, and I need all the help from the racing capital of the world and its periphery to make this happen. Autonomous racing itself is, who knows, it could become a sport. I want to believe there's an audience for it. There's this audience for it. Everybody is in on AI, and they want to know what AI is doing, how it influences their life. The opinions are divided. It couldn't be a better time. Now, my goal is not to replace the thrill of human motorsports. That's not what anybody in pit lane wants to do. I can guarantee you that. We are there for the research, for pushing the frontier of robotics. But if it's entertaining, then can you blame us? I don't know. So in many ways, we are just getting started, right? We started with a single car, we did 2 cars, now multi-car. This is what human drivers can do. This is Kimi Raikkonen, Ferrari driver. Look at every driver, not just him. Look at how fast they are driving and brake checking each other, still being able to assess risk, figure out what has to be done, keeping it controlled, keeping it together. Somebody locked their wheels, no big deal, continue. You touch my wheel, it's fine. In Indy, this would be the end of the race if this happened. We are not even close. We've done so much work, we are not even close to what human racing drivers can do. But we are trying. This is what we tried in January. This doesn't look as exciting and close proximity as the previous video, but this is where state-of-the-art autonomous racing is today. We are trying to get to that level because that is what I believe we need to solve in order to really solve the physical intelligence part of it, to be able to be even comparable to human level driving and expert human level driving. So my goal is to race against the best drivers, whether the best driver is an AI or a human. And we are just getting started. And I would like to close by asking you, if we go back to the beginning of this talk and understand why AI is not able to solve driving, who would you want driving your AI car? The average American driver skill or like the best driver skill? What should be the litmus test, the benchmark for autonomous vehicles? We may have many different answers. I'll share my answer, that my goal is to create the grandmasters of autonomous driving. That's what I'm in it for. So sorry for exceeding my time, but I'll end here. Thank you so much and for your patience and for staying up. Thanks. This is Madhur.
All right, thank you for very insightful and great presentation. Now we have time for a few questions. If you have a question, raise your hand, and when you're speaking, please use the microphone.
Information overload, I get it.
Madhur, thanks for the awesome talk. One of the things that's interesting is this idea of safety versus pushing the limits in terms of new advanced algorithms, right? So, you're an open book. How do you guys evaluate that? If you've got a new, state-of-the-art machine learning AI algorithm, what's your process that you do to put it on the car?
I think the short answer is simulation. I'm pretty confident that 95% of the stack which runs on track has been tested in simulation at some point. But you know how it is. Sometimes in the moment you have to fix a problem and there's not enough time and you have to qualify tomorrow or maybe not try and then you just roll with it. So there is definitely that reality, but the single biggest factor which has helped us decide both the spectrum of safety versus how much to push, and also just the choice of what to go with has been simulation. Yeah. And so this is the reason why we never fully gave into a single simulator, because every single time we would commit, a question would arise that this simulator would not be good at, and then we would like, okay, now we need a different simulator to just try to answer this planar question, which D-space cannot answer or this cannot answer. Yeah. So there is actually like a very, I didn't talk about it, but there's a very real sim2 real problem here that could be well studied. Yeah.
Yeah, so it's more like a high-level.
I can hear you. Yeah.
Okay, yeah, it's more like a high-level question, but for example, for human drivers, we have a sort of common sense that if you're on a highway and you're next to a semi-truck, you probably don't want to keep next to it for a prolonged period of time because there's a larger probability that something might happen, right? So when training, say, self-driving vehicles for those purposes, well, racing included, right? How can you, in addition to just giving a lot of data to it, how can you encourage those kind of activity that promote safety?
Yeah, it's a very good question. For the commercial AV world, as far as I know, we do deal with different agents differently. If it's a truck, someone has encoded, whether through data or through just baked in engineering, that you shouldn't be in the blind spot of the truck for a long time. It's probably unsafe. And also, if you look at human data, we don't tend to sit in that spot for a long time, so you could learn that behavior from the data. For racing, I may want to mold your question and you tell me if that's what you meant or not. There is an element that has starting to emerge, even in 4-car racing, or 2-car racing, where different teams or different AI drivers have different personalities. So we know some teams, their choice of race lines or their throttle response could be learned because we've raced against them many, many times. So we could tailor, I'll tell you the bottleneck that we have right now. We can distinguish with the multi-car when we did the racing. We could say that there are 2 cars in front. This is prediction A, prediction B. Today, I cannot tell you that prediction A is this team and prediction B is this team. I cannot recognize their number. Maybe I can based on the color. We just haven't tried it yet. But you would have to be able to get your perception to that level where you not only know how many agents are in your proximity, but who is that agent. And then there could be a memory or a library of agent behavior that you have learned or baked, like we have done with the trucks, that could be invoked in your strategic plan of the race. So it's doable. It's an interesting thing to explore. Yeah. Yes, please.
So this personality that you mentioned is very interesting. So do you think this is more of a result of the algorithm choice of the researchers, or it's something learned by the intelligent part against the other racing cars, for example?
As much as I like the prospect of the latter, I think for sure it's the former. It's the personality of the team, their mentality of their algorithms and their choices, which ultimately the sum of the parts is what I'm describing as the behavior or the personality of the car. But if we start, there is, when you have multiple cars, it's an unsolved problem really, right? So because racing is unstructured, and one criticism that we often get is, why is your perception problem so difficult? Because there's no traffic signs, there's no lane markings. This should be just easy peasy, right? So why is it difficult at all? And my response to that is, the reason we have traffic signs and lane markings is because they impose behavior on others. That's the only reason we have them. It's for the humans. So when I see a traffic sign, it's helping my mental model predict better what I expect others to do, because they have also seen the same sign. So when you actually remove the clutter, you are removing clutter, so you may be simplifying perception, but that's very myopic. You are removing clutter and you are adding uncertainty, because now all bets are off. We don't know what anybody's going to do because there's no guiding principle there. So derailed what you asked, but in many ways, that is the unsolved part. How do these Formula One drivers, they have been racing go-karts since they were 6 years old, and they have just built this mental model of judging the personality of the other driver, right? There's, in the limited chances I've had to interact with real Indy drivers, they've always told me that how when they were rookie drivers, they used to get bullied by aggressive drivers because they could just like bully them into making a mistake. That's like so nuanced. What kind of expertise do we have to unravel to even reach these kind of questions? I have zero idea, but you know, that's why I'm always of the opinion that we've barely made a mark here. Yeah.
Okay, one last.
Last question. Okay.
Could you talk a little bit about how you developed your push-to-pass strategy at Las Vegas?
So for context, in the final race, there was something called push-to-pass, where you know, once per lap you could demand some high throttle or some elevated throttle, because otherwise, you know, these cars are at a level where everybody can go fast. There would be zero overtakes. So the answer is what I've already said. We simulated. So we developed basically we have a simulator which is not as, you know, photorealistic. We don't care, but it just models the other agent as a square in MATLAB, for instance, and then we can choose what line the opponent is running, what line we will run, and we can tweak what push-to-pass zones they might have and what should be our push-to-pass zones. So the strategy, to give you a definitive answer, was that we realized that being on the base throttle and going to 35% doesn't give you massive advantage. It's basically going from 75 miles per hour to 80 miles per hour at 5% throttle. The real advantage comes from the 100% boost that you can demand for 2 seconds. So how should I make it succinct so that I don't take too much time? 1 lap at LBMS was 52 seconds. The push-to-pass is you get 2 seconds of 100% boost, followed by 28 seconds of 35%, followed by 20 seconds of cool down. That's already 50 seconds gone. So if you use push-to-pass once entirely, you can use it once per lap. But if you want to use it twice, let's subtract 40 seconds from the lap time, because you will have 2 cool downs. You are left with about 12 seconds per lap. So you just use push-to-pass 5 seconds on the front, 5 seconds in the back, because you really want to exploit the 100% throttle. That's what we were doing. So we ran out of push-to-pass literally on the last corner. If we had push-to-pass, it wouldn't have been as photogenic as a finish that. But you know, I like the finish. It's an exhibition race. It made it very interesting. Yeah.
Right, once again.
Yeah. Thank you so much. Yeah. Thank you.
All right, then. Thank you for everyone attending today. This concludes our seminar today. I'm looking forward to seeing you at the next seminar in the country. Right, thank you so much.